This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, good afternoon everyone. When you're ready, we'll make a start. So the plan today is to look at problem set 5. This is the last problem set. And I guess it might be worth noting that the sort of questions we'll be looking at today are not dissimilar to the sorts of questions that appear in the second part of the exam usually, as questions 3 and 4. Okay. In fact, the second problem we'll look at was in an exam many years ago, maybe 2012 or something like that. Okay, but at that time the exam had a slightly different structure, so it wasn't in the second part; it was in the first part. All right, but there's the sort of questions we're looking at now are a good indication of the sort of things that happen in the second part of the exam. So, both questions are about designing compensators that are part of a feedback loop that is trying to achieve some sort of control objective. The first problem is about controlling the position of a mass. Okay. This mass floats on a bed of air, okay, so that there's no friction forces, okay, and it's inside a rail, right, so we're just going to get linear motion, and we're assuming that there are no friction forces due to the rail, and there's no friction forces underneath because it's sitting on a bed of air, and there's an actuator which can provide a force in the direction of a measured displacement. Okay, so the force is produced by spinning a propeller, okay, and you can you can set the force imparted by spinning the propeller by making the propeller go around at the right speed. Okay, and we're measuring the position of the mass using an ultrasound sensor. Okay, and the questions are really about, you know, what you can do with different types of compensators, right? So start off with a proportional gain controller, then look at a lag controller, then look at a lead controller, and then another type of lead controller. And what we're trying to achieve are certain closed loop specifications expressed in terms of a desired phase margin and crossover frequency for the open loop transfer function, which, as we know, is just the product of the controller and plant transfer functions. So the plant transfer function in this case is a relationship between the force imparted by spinning the propeller, okay, and the position of the mass. So simply applying Newton's second law gives us a relationship between the force and the position, okay? So Newton's second law says that the mass times the acceleration is equal to the force, so the acceleration, which is the second derivative of displacement, will just be the force divided by the mass. I think later on, the mass is just set to 1 anyway. All right, so we've got a plant, and the plant has a transfer function that's 1 on s squared, right? And the output is the position, all right? The input is the force, okay? And the text there suggests that there will be a difference between what can be commanded and the actual force imparted, and that might be due to a mismatch between the relationship that tells you how fast you have to spin the propeller to get a particular force, right? So there's some error there, some uncertainty, and we're modelling that uncertainty as an additive perturbation that results in the force actually experienced by the mass to a command, right, that will be set by the controller, right? So there's just modelling some uncertainty between a signal that can be set, right, and the force that will be experienced, all right? And the command is generated by a controller, okay, which will be looking at the difference between a reference signal and a measurement of the position. Okay? All right. So that's the closed loop. If you wanted to account for, we're getting this plant transfer function by saying, well, x double dot is f, right? So we take the Laplace transform, we get s squared xs equals fs, assuming there are zero initial conditions, right? But if you included the effect of initial conditions, then you'd be getting s squared xs minus sx naught minus x dot naught equals fs, all right? And these signals here could be, or these non-zero initial conditions could be, added in as additional input disturbances or output disturbances. Okay, so that's how initial conditions might affect the closed loop. All right. If we had, for example, zero initial velocity, right, that term would go away, but a non-zero initial position, then when rearranging this to look like x of s is 1 on s squared f of s, we would get plus x naught on s, right? And so we could add that in as something that adds on, right, here, so that we've got this signal here being this part, and then this signal here being this part, and that would be like a step output disturbance. Okay? All right, so, I think that's not really part of the questions here, but I just want to point out that, these exogenous inputs, in this case, this guy is representing some uncertainty. It's uncertainty between a command which might set the speed of the fan or the square of the speed of the fan, which will be related to the force, but with some parameter uncertainty. All right, and we're saying, well, that's a plant input disturbance, and we could get a plant output disturbance by virtue of there being a non-zero initial position. Okay? All right, so the first question is saying, well, what can we do with a constant gain controller? Okay. Is it possible to achieve closed loop stability with just a constant gain controller? Well, if we've just got a constant gain controller, then our characteristic polynomial will look like s squared plus k, where k is the gain of the constant controller. All right? And so, that will have zeros at s equals plus or minus j root k. And no matter how we choose k, they will always be on the imaginary axis. All right? And that's consistent with what we would expect by drawing, the root locus plot, right? We've got two open loop poles at 0, okay? And this is the real axis and this is the imaginary axis. We have no finite zeros, right? Our plant transfer function g of s is 1 on s squared, right? But there will be zeros at infinity. There will be 2 of them because the relative degree here is 2. All right? And we know that for small values of k, we'll end up with closed loop poles that are close to the open loop poles, all right? But we have to satisfy the phase condition that defines the root locus. And in order to satisfy the phase condition, the closed loop poles will be moving away from the open loop ones at angles of -90 and +90, and we go towards the zeros at infinity along the imaginary axis as we increase k, right? So that's consistent with, the roots of the characteristic polynomial always being on the imaginary axis, right? So for any value of a k, you get two closed loop poles, and where they lie will be at plus j root k and minus j root k. All right, so we can't stabilise the system, so we certainly can't satisfy these performance specifications, because these are only meaningful, if we have a stable closed loop. So the next question is asking, well, what can we do if we now use a more sophisticated compensator, feedback compensator, which in this case, by virtue of this relationship, will be a lag compensator, right? So it's a lag compensator because the time constant associated with the pole is greater than the one associated with the zero, right? So if you drew a root locus type plot, we would be looking at a situation with that compensator that looks like this. We'd still have the two zeros, the two poles at s equals 0, right, from the plant, and we would have another one due to the controller and a 0 that is further away from the imaginary axis than the pole due to the compensator. Okay, so if you thought about the root locus here, what's going to happen as we start increasing the gain term, this guy here, from the compensator. All right. So these parameters here fix the location of the pole and the 0. So this is -1 on tau p, and this is -1 on tau z. Okay. So we know from the rules for drawing root locus that, which is really about satisfying the phase condition, that for any value of k, we're going to get two closed loop poles. All right. Sorry, hang on. How have we got here? We've got three. We've got three closed loop poles, right? Because there's three open loop poles. So when you write down the characteristic polynomial, it'll be cubic, right? So there's three zeros of the characteristic polynomials. The zeros of the characteristic polynomials are the closed loop poles, right? If you write down what the characteristic polynomial is, right? It's this AS times LS. They're the denominators of the plant and the controller, right? BS, PS. Okay. So the degree of the characteristic polynomial is really determined by this product here, because we start with a proper controller and plant transfer function, right? And the order of this will be the number of open loop poles, right? Because the zeros of A are the plant poles and the zeros of L are the controller poles, okay? All right, so we're going to get three values for each value of the compensator gain, right? For small values of the compensator gain, we'll end up with one close to this open loop pole, right? And we'll get one close to this open loop pole and one close to this open loop pole. All right, as we increase k, this one will stay on the real axis because it sits to the left of 1, 2, 3, right? And move towards the finite 0 at s equals -1 on tau z. All right, so one of the closed loop poles is stuck on the real axis between the controller pole and the controller 0. All right. These guys will have to split apart in order to keep satisfying the phase condition, right? For small values of k, they will be departing at angles of -90 and +90, all right, in order to satisfy the phase condition, because the phase due to these guys is adding up to something close to 0, right? So they're not going to contribute. So, we need to be on here to satisfy the phase condition. So they'll move away like this, all right? And they'll move towards asymptotes that the root locus will approach as k becomes large, right? And those asymptotes are anchored at the sum of the poles minus the sum of the zeros. These are the open loop poles and open loop zeros divided by the relative degree. The relative degree in this case is 2, right? Because we have 3 poles and 1 0, so n is equal to 3 and m is equal to 1, all right? And, we've got a pole at minus 1 on tau p, and then we've got a 0 at minus 1 on tau z, all right? But that will be a positive number, all right? Because, look at the magnitude of minus 1 on tau z, right, which gets added here by virtue of the 2 minus signs, right? So this will be a positive number. So the asymptotes will be anchored at a point on the real axis in the right half plane, all right? And one of the closed loop poles will approach the asymptote at an angle of pi on 2, and the other will approach an asymptote at an angle of minus pi on 2, right? And you can check that, no matter what we choose for the gain, these guys will always be in the right half plane, right? So in principle, you could just write down what the characteristic polynomial is, but it's a cubic, right? So it's going to be hard to analytically write down where the poles are, all right? But you could exploit, the fact that that, this one's always on the real line to figure out where these guys are, right? If you look at a Bode plot, right? So the open loop transfer function in this case looks like k tau zs plus 1 on tau ps plus 1 times 1 on s squared, right? So that's our open loop transfer function, which we've been denoting by lambda s, right? So if we looked at the magnitude of lambda when evaluated at s equals j omega, and here we're plotting log omega, that's what we plot on a Bode plot, right? Then, this guy here is going to give us something that's, going down at 40 dB per decade, so it's going to go down by 40 for 10 across this way, right? This guy, by virtue of the relative position of the pole and 0, is going to, the pole's going to kick down at a particular frequency, right? And then the 0 is going to kick in to flatten it off again, right? So we're going to end up with something that, in total does this, and then it goes down, right? And then it'll run parallel, okay? And changing the location of the pole and the 0 just changes where this kicks down and where this flattens off again, and they'll move around to the left and the right depending on how we move these to the left and the right. All right? But if you look at the phase, you can see that what happens is that the phase due to the double integrator will always be at minus pi, all right? And the lag compensator will always be giving you phase lag, right? The pole makes the phase negative, but then the 0 makes the phase positive and brings it back up to 0, right? And where this kicks down depends on the location of the pole, and where this kicks back up again depends on the location of the 0, right? Pull them further apart, this will go down further before it comes back up. But no matter how you choose them, right, the overall phase is always below minus 180, right? So no matter where you choose, set the crossover frequency to be, sorry, I should have drawn that in black, right? You're always going to get a negative phase margin. You're always going to be below minus 180. Okay. And if you think about what the Nyquist plot might look like, you will see, so the Nyquist plot is just a polar plot of this, really, right? And you'll see that by virtue of the phase always going beyond minus 180, you'll start off here, right? At very low frequencies, but as you increase frequencies, you'll move into this quadrant, right? Because this quadrant, this is minus 90, minus 180, so this is less than minus 180. This is like going below. You're going to end up in this quadrant, all right? So we're going to go this way towards the origin, right? And it's not going to, it's going to come in and approach the origin with a phase still of minus pi, but it's going to go up, right? And then, so that corresponds to going up the positive imaginary axis, which is part of the Nyquist D contour, right? We've got to make a little indentation around the two poles at s equals 0, right? But going up this part of the Nyquist contour will give us something that looks like this, which is consistent with the phase going below minus pi, which pushes us into this quadrant, right? And then, as we go around here, the magnitude is 0 because this is strictly proper, all right? When we come out the other side, by virtue of this being a real rational function, we just get the mirror image, right? So it'll come like this. Whoops, it'll be the mirror image. Let me draw it again. Drawing it backwards is harder than drawing it forwards. Okay, so it's going like that, all right? And then as we go around this little indentation, we're going to get a net change of minus pi radians for every pole we have inside that little indentation. So we're coming up here, right, by moving along like this, right? And then we get 1 times minus pi for one of the poles and then another minus pi for the other, okay? And you can see that what's happening is that we're ending up with clockwise encirclements of the critical point. The critical point will be inside here, right? No matter how you choose the location of the controller pole and 0, no matter how you choose the gain and make this shrink and expand, right? The Nyquist plot will always look like this, giving you 2 clockwise encirclements of the critical point, right? Which is entirely consistent with always having 2 closed loop poles in the right half plane, because the number of open loop poles in the right half plane is 0. Right? So for stability, we want 0 encirclements, but no matter what we do, we'll end up with 2, right? Which is what we saw here. Okay? What else can we do? So the next bit is about saying, well, okay, what happens if we now consider a lead compensator? Right? As we've seen, a lead compensator can help us move asymptotes to the left, right? A lag compensator always pushes asymptotes to the right, which is the problem here, right? It's made things worse than having no compensation other than a constant gain. It's pushed these are asymptotes here, along which the root locus approaches the zeros at infinity, and the lag compensator here has pushed them into the right half plane, causing closed loop instability. A lead compensator does the other thing, right? So with the lead compensator, the 0 of the compensator is closer to the imaginary axis than the pole. And in this particular case, we've chosen, you can see that the time constant associated with the pole is 1/9 the time constant associated with the 0, right? So this is almost like, this is not to scale, right? This is 10 times further away than the 0. So as we increase k, this pole moves towards that 0 like that. So that is kind of similar to the lag compensator case, all right? But now these two, when they split apart, they go towards asymptotes. And the asymptotes, in this case, are now, minus 1 on tau p minus 1 on tau z. It's the same as before, divided by 2, but now this is a negative number. All right? So the asymptotes, which are approached by the root locus as k becomes large, right, as the root locus moves towards the zeros at infinity, because we have 2 of them by virtue of the fact that the open loop transfer function is relative degree 2, will now be anchored at some point in the left half plane, right? And really, this distance here is just this distance divided by 2. Right, so we can control where these are by changing the location of the pole of the compensator. If we push the pole further that way, the asymptotes will move further that way. Right, so as we increase k, we've always got 3 poles. One of them will be here, right? The other one will be along this line going towards the asymptote at an angle of plus pi on 2. This one will be going towards the asymptote at minus pi on 2. They will always be in the left half plane. All right? So if we think about what will happen to the Bode plot, well, the Bode plot will change relative to these guys, right? Because now, the red line's the same, right? That's just the double integrator here, right? But now we've changed this part, right? And we've changed this part in such a way that the magnitude part will do this, right? The 0 kicks in first, then the pole flattens it off, right? Where this happens relates to this guy, where this happens relates to this guy in the case of a lead compensator, right? So now this guy will look like this, right? But we can change where this is by now shifting everything up and down by the same amount at all frequencies by adjusting k, right? But most importantly, the phase characteristic for the lead compensator is now like this. It's always positive phase instead of negative phase. And so the overall phase response will be like this. And no matter where we choose the crossover frequency to be, we'll always get a positive phase margin. How much? Depends on where the crossover is. All right? So the lead compensator gives you stability, right? So what happens to the Nyquist plot? Well, the Nyquist plot, in this case, will look like, we still start off at minus pi, so we still start off somewhere down here at infinite magnitude, right? Because at 0 frequency, 1 on the s squared when s is evaluated at j omega, and you set omega to 0 is infinite magnitude, but the phase is minus pi, so it's somewhere down here at infinite magnitude, right? We don't get quite the infinite magnitude because we put an indentation. We're never quite at 0 frequency. We're at plus epsilon or minus epsilon, okay? But because the lead compensator now pushes the phase this way instead of this way, right? It goes like this, right? Whereas with the lag compensator, it went like this. It went into this quadrant. Now, the lead compensator pushing the phase like this pushes you into this quadrant, right? So we've gone up, this part of the D contour, right? Now we're going to go around the bit at infinite radius. You get stuck here. When you go up the negative imaginary axis, you come out the other side like this, the mirror image of what you had before, okay? Now we've got to go around the little indentation around the two poles. Okay, the same thing will happen. We'll get a net change in phase of minus 2 pi because there are two poles inside the little indentation. So as we go around the indentation, we get 1 due to one pole and another minus pi due to the other. Minus 1 is inside here. How many encirclements do we have? 0. We don't encircle that point. We go around it, right? But we don't encircle it. Unlike this case here, where we definitely encircled it twice. Right? The phase is never, this never intersects the real axis. Right? So we get no encirclements, no matter how you choose the K, no matter how you choose the location of the pole and 0 in the compensator, you'll always get this shape that makes no encirclements. Right? So the lead compensator can stabilise. Right? And the other two parts of the question are about saying now, well, how do we choose the parameters of the compensator in order to achieve our phase margin and crossover specifications? Okay, in this case, there are only two parameters to choose, right? Because we've fixed the position of the pole relative to the position of the 0, right? So there's only one parameter here, and then the other parameter is K. So if you go and look at the solutions, which are written up here somewhere, okay, it shows you how you can go about writing down some equations that constrain the controller parameters, right? So that you can then solve those equations to find out what parameters will meet your specifications. So one of the specifications was a crossover frequency of 3 radians per second. The crossover frequency is the frequency where the magnitude of the open loop transfer function is equal to 1, right? So that will give us one equation that we can just write down that constrains the controller parameter K and the controller parameter tau Z, right? So if you like, this is a constraint on the controller parameters coming from our specification that the crossover frequency should be 3 radians per second. Okay? All right. The other part of the specification says we want a phase margin of 45 degrees. The phase margin is about the phase of the open loop transfer function at the crossover frequency, right? And in fact, the phase margin will be, if this is in radians, will be pi plus the phase, right? We're measuring how close this is to minus pi. In fact, we're trying to see how much above it is, right? So if we want this to be equal to 45 degrees, so make this 180 so that everything's in degrees. You've got to make sure everything's in degrees or everything's in radians. You've got to pick your units and stick to it, right? So what's written down here in the solutions is in degrees, so let's stick to degrees. So we've got to measure the phase in degrees, right? So the phase margin condition is basically telling us that this needs to hold when omega c is equal to 3, right? So it's telling you that the phase of the open loop transfer function at 3 radians per second must be equal to 135 degrees, right? Saying I want the phase to be 45 degrees above minus 180. That's what the phase margin specification is telling you. So that allows you to write down another equation that constrains our controller parameters, and in this case it turns out to only constrain the parameter tau Z, right? Because our open loop transfer function is K tau Z S plus 1 on tau z on 9s plus 1 times 1 on s squared. And if I look at the phase of that, that's equal to the phase of k plus, the phase of 1 on s squared plus the phase of the compensator pole and 0. Okay, k is a positive number, so that's just 0. Right? We're going to be evaluating this on the imaginary axis somewhere, and no matter where we evaluate it, the phase of this will be, minus 180. All right? And then we're left with this phase here. So that's where the 180 here is coming from. It's why you don't end up with a dependence on k, because it just doesn't influence the phase, given that we know that k has to be chosen to be positive in order to achieve closed loop stability. All right? And then this is just an expression for what the phase of this is, right? By writing that when evaluated at s equals j omega c, with omega c equal to 3, expressing this ratio of two complex numbers as a product of two complex numbers by multiplying the top and the bottom here by the complex conjugate of the bottom. So what you get on the bottom here is just the magnitude of the bottom. There's the complex conjugate of the bottom. All right? The phase of all this will be the phase of 1 over this positive number, so that'll be 0 again, plus the phase of this product of two complex numbers, right? This product of two complex numbers will have, an imaginary part that looks like tau z3 minus tau z on 3, right? And it'll have a real part, right? That will be 1 plus tau z. Whoops. Okay, and we know that the phase of a complex number is the arctan of the imaginary part divided by the real part. Okay, and the imaginary part is 8 tau z on 3, and the real part is 1 plus tau z. It should be tau z squared. Right, because when you multiply that by that, you get the tau z squared. The 3's cancel out. So now we have, two equations constraining our two parameters. In fact, this equation just tells us what one of the parameters is directly, right? Our desired phase margin is 45 degrees, right? If I take the tan of that, you get 1, so that gives us a quadratic equation now. So there are two possibilities for the location of the 0, all right? And then there will be two corresponding values of k that will satisfy this equation once we've fixed tau z, right? And if you think about what the lead compensator is doing, it's doing this with the phase, and one choice puts the phase there with the crossover frequency there, and the other choice puts it there. They're the same number, right? It's giving you the same amount of push up from minus 180, which you always have because of, because the phase of the 1 on s squared is always minus pi. All right, so again, this is just an example. It's not a recipe to follow. It's just an example of how you can use information contained in your specifications to write down constraints on your controller parameters that then allow you to fix the controller parameters in order to meet your specifications. All right. So the last part there is just about saying, well, we've got a different parameterization of our lead compensator now, which involves the three parameters: the gain at DC, right? K is the gain of the controller at DC, right? Because when I evaluate this at s equals 0, all I get is K, right? So that's one parameter. Then I've got the location of the 0. That's another parameter. The location of the pole. That's another parameter. So now I've got 3. I've only got 2 specifications, right? Phase margin of 45, crossover of 3 radians per second, but I've got 3 unknowns. I need another specification. And in this case, the other specification is that, you know, you want the third closed loop pole to have which lies on the real axis on the basis of the locus analysis that we've done, to be 10 times further to the left, right, than the 2 poles that appear as a complex conjugate pair, right? Why might we have a specification like that? Well, because if that's the case, then the closed loop response will be dominated by the conjugate pair of poles, right? And so it would then be reasonable to approximate the closed loop complementary sensitivity function by canonical second order dynamics. And we've seen how in that situation, when that's a good approximation, we can translate our crossover frequency and phase margin specifications. Well, we've been going the other way, but you can go backwards, right, where you can take on the basis of that assumption, your phase margin and crossover specifications back into a desired damping and natural frequency for your dominant second order dynamics, right? And if you do that, you get that, you know, you want this much damping and this much natural frequency. That will be consistent with the phase margin and the crossover frequency specification. I think these need to be updated. So that fixes part of your characteristic polynomial to give you the 2 dominant poles in the closed loop, and then you're told that the other one has to be 10 times faster, which means the real part, right? And the real part of the closed loop poles due to this part of the characteristic polynomial is given by this, right? So that now fixes that, okay? So you now have what you want. You've translated your closed loop specifications, originally expressed in terms of desired phase margin, desired crossover frequency, and where you want the third pole to be relative to the 2 dominant ones, right? That tells us what the characteristic polynomial should look like, right? And this is what the characteristic polynomial looks like for the compensator and plant that we have, right? So then you just have to match coefficients to figure out what the parameters are. Okay, simple as that. So just again, it's just an example. It's not a recipe. It's an example of how you can use information to write down constraints on the parameters that you're trying to fix. Okay? There will be a question like this in the exam. All right, so the problem 2, right, is about a feedback amplifier. So this is a 2-port network model of a feedback amplifier. It's a different way of writing down something that might be more familiar to you, that looks like this. There's an op amp, there's an input voltage which is referenced to ground, right? There's a resistor going to ground, another resistor like that, a box in here which provides some compensation for the feedback, right, to the negative terminal of the op amp, right? So this is V in, this is V out, this is VM, and this is VF, right? It's a measurement of V out, effectively. So the F here is like this little resistor divider. The C is a resistor capacitor network put inside this box to provide different types of compensation for the feedback path, right? So this is a 2-port network representation of this. Op amps have dynamics. They don't just have gain, they have very contrived dynamics, right? They always have 2 poles, right? What's important about an op amp is it'll have very, very large gain. But they are designed in such a way that they actually have 2 poles positioned very carefully, right? So that you can wrap, resistor divider networks around them and always end up with a closed loop that's stable. All right? So a model for the relationship between the voltage across the input terminals of the op amp and the output, everything referenced to ground, will be a transfer function that looks like this. Okay, and if you drew the Bode plot, it'll be something that has very large gain at DC. Then there will be a pole. So you go down at 20 dB per decade, and then there will be another pole. And in this case, I've chosen the gain to be such that where this other pole kicks in to give you 40 dB per decade, the op amp gain will be 1. Right? So op amps aren't just constant gain across all frequency. Right? Op amps have variable gain across frequency. All right? All right. So this question is really saying, let's consider what happens when there's nothing in this box. And so all you have is feedback of a fraction of the output voltage to the negative terminal. That fraction is determined by the ratio or the relationship between, this is a resistor divider network, right? So you always get some fraction of V0 being fed back like that. And then it says, well, what happens if I put a resistor capacitor network in here that has a lag type characteristic, and what happens when I have something that has a lead type characteristic? All right, so that's what this stuff is about, right? Putting nothing in that box, putting a lead thing in that box, putting a lag thing in that box, right? So in terms of a block diagram, what we're dealing with here, just by writing down the equations, right, we're saying, well, Kirchhoff's voltage law around here says that I have VI minus VF gives me VM. That goes into a box that has a transfer function AS, that's the op amp, to give me V out, right? And then that's being fed back through a box that gives a relationship between VF and VO. And that is F, which is the resistor divider fraction, right, times the compensator that I put in that little feedback path, right? So, the closed loop transfer function from here to here will be AS divided by 1 plus FCS AS. All right? And by virtue of A having very large gain at low frequencies, the characteristic of the feedback amplifier gain at low frequencies is really determined by F, right? Which is what's written here, okay? Because, if we write, we've got A on 1 plus FCA, well, that's, 1, take the A out, take an A out here, we've got 1 on A plus FC, right? So that goes with that. When A is very large, this is approximately 1 on FC, because that will be very small. And so what you achieve with a feedback amplifier like this, when you have very high gain through the op amp, is control over the closed loop gain, determined mainly by the feedback resistor divider network, right, which you can make very precise. It's very hard to build op amps with very precise gain characteristics, right? You might buy 2 op amps from the same manufacturer, and one will have a Bode plot that looks like this, and one will have it that looks like this, right? What matters is that this is big, and when this is big and you wrap a feedback network around it, the gain from here to here is mainly determined by this guy here, which you can make very precise. So you can buy very precise, they're called attenuators, right, that allow you to set this ratio very precisely, right? And that determines, the closed loop behaviour, at least at low frequencies where A is very large. Right, so that's why we have feedback in amplifiers. Okay, it's to deal with the fact that it's very hard to build this block to have precise characteristics. In fact, the characteristics wander around with changes in temperature, all sorts of things. Okay? All right. So this is what the Bode plots look like. I think the only trick here is that in order to get everything onto the same plot, right, I've drawn minus the lead compensator, right? Otherwise, I would have had to draw the phase bit up here. Okay, so by multiplying the phase of the phase lead compensator down here, I've just multiplied it by -1, which shifts it down by 180 degrees of phase, because that's what the phase of -1 is. All right? But you can see that this is what I drew for A, right? The lead compensator has gain that kicks up because the 0 kicks in before the pole flattens it off. It always gives you phase lead. Remember, this should be really up here. Whereas the lag compensator reduces the gain, right, because the pole kicks in before the 0 flattens it off, and it's always giving you phase lag. All right? Now, the open loop transfer function, lambda, will be the product of F, the compensator, and A, right? What happens on a Bode plot when you take a product? Well, things add up, right? So if I've got F is equal to 1, that'll be a line here at 0 dB, right? But remember, F is always a number less than 1. It's a number between 0 and 1 because it's a resistor divider, right? So it's always a fraction of 1. So if it's 1, F will be a line across like this, right? If F is 0.1, then F will be a line like this, all right? And so on. And so to get the open loop Bode plot, you've got to add up all the components, right? That's the advantage of working in dB, right? Because logs of products are just sums of logs, okay? Phases always add up, right? And so, the phase of the resistor divider thing is just 0 because it's just a positive number between 0 and 1, right? But you would have to get the phase of lambda, you would have to add the phase of A to the phase of the lead compensator, which is really up here. It's just drawn down here for convenience, right? Or if it's the lag compensator, this phase here. So, in the proposed solutions, it's just saying, well, when do I get a phase margin of 90? Right? In the case where there's no compensation, just the resistor divider network, right? So, here when I'm adding to this, right? With F equal to 0.1, right? I'm going to bring this down. Bringing this down is like moving the 0 dB line up. So all I'm doing on those other plots is moving the 0 dB line up rather than pulling A down, right? To figure out how the crossover frequency moves for different values of F, right? So these lines are like, here's when F is 1, right? When F is the square root of 0.1, F is down here, right, at minus 10 dB. So when I add that to A would move down, but that's like saying the 0 dB line has moved up to here. Okay, so that's all that's happening here. And you can see for different values of F, you end up with different crossover frequencies, right? The crossover frequency will be here when F is this fraction of 1. It'll be here when it's this fraction of 1. It'll be here when it's this fraction of 1. Right? So rather than moving this around, I've moved the 0 dB line around. That's all. Okay? To figure out how the crossover frequency changes as I change F. All right? Now, of course, we're looking at the crossover frequency because that's what we have to figure out first before determining what the phase margin is. The phase margin is related to the phase at the crossover frequency. For different values of F, we're getting different crossover frequencies, and therefore getting different phase margins. F doesn't change the phase of the open loop, right? So we just get the phase of A, okay? And you can see that when the crossover frequency is here, we'll end up with a phase margin of 90. When the crossover frequency is here with F equal to 1, we get a smaller phase margin. So you'd expect more oscillatory response, okay? But as we keep making F smaller, we get more phase margin.